Have you ever stared up at the vastness of the night sky and felt a shiver of curiosity about how it all began?
Oh, absolutely.
Or maybe felt the solid ground beneath your feet and wondered about the hidden, fiery depths shaping our world?
It happens, yeah. Or seen a hurricane on the news and just thought, wow, what is that?
Exactly. Understanding the forces behind it all.
It's really remarkable, isn't it? You think about everything from the cosmic dust that, came together to form our solar system
Right.
to the intricate network of rivers carving landscapes right here on Earth. Everything is so connected.
And understanding those connections, it's not just about knowing facts, is it?
Not at all. It unveils a deeper, well, a more profound appreciation for our planet. It really does.
That's exactly what we're setting out to do today. We're embarking on a pretty comprehensive deep dive into the fundamental concepts of geography.
Yep.
We've gathered a rich stack of sources, and our mission really is to pull out the most important, maybe surprising, and insightful nuggets of knowledge for you.
Think of it as your shortcut to being genuinely well-informed, maybe. We'll unpack everything from the mind-boggling origins of the universe and the dynamic ballet of our solar system, right down to the hidden layers deep within the Earth.
We'll explore the powerful forces that are constantly sculpting its surface, creating everything from towering mountains to those vast flat plains.
And we'll also plunge into the intricate systems of our atmosphere and oceans, exploring the invisible engines of global wind patterns and the mighty flowing ocean currents. It's all connected.
And then we'll zoom right in, exploring the fascinating geography of India specifically, and connecting it back to these broader global patterns.
Right. The goal is for you to walk away not just informed, but, well, genuinely intrigued by the magnificent forces that define our shared planetary home.
So let's unpack this. All right. So our journey begins not just at the beginning, but with the Big Bang Theory.
The big one.
Yeah. This is the widely accepted explanation for the origin of our universe. It pictures our entire cosmos starting as an infinitely hot and dense single point.
Hard to even imagine.
Right. And then, roughly 13.6 billion years ago, it just expanded rapidly outwards. All of this from one tiny energetic point.
It's a concept that really stretches the imagination, definitely. But it's backed by decades of scientific inquiry. The foundational ideas were laid by people like George Lemaitre back in 1931, who first proposed the expanding universe idea.
Okay.
And crucially, Edwin Hubble's observations provided key evidence. He saw distant galaxies moving away from us. And the farther they were, the faster they were receding. This phenomenon, known as the expanding universe, strongly supports the idea of an initial Big Bang explosion.
So, in a way, we're kind of living inside an ever-inflating cosmic balloon.
That's one way to think about it, yeah.
And the scientific field dedicated to understanding this vastness, the evolution of everything around us, that's called cosmology.
Correct. Astronomers and scientists are, tirelessly trying to decipher the universe's scale, its underlying structure, maybe even its ultimate fate. It's really mind-boggling work.
And within that unimaginable vastness, we find our own galactic home, the Milky Way.
Our little corner. It's classified as a large, barred, spiral galaxy, just a colossal collection of billions of stars, plus gas and dust, all held together by gravity.
And our sun is just one star among countless others in this massive swirling structure.
Exactly. And the scale really hits home when you consider our cosmic neighbors. Like, the Andromeda Galaxy is our nearest major galactic neighbor.
Right. Just thinking about other galaxies out there, each with billions of stars, it really puts our place in the universe into perspective, doesn't it?
It absolutely does. It's not just our galaxy. There are countless others out there. Each one almost a universe in itself.
It definitely emphasizes the sheer staggering scale.
Okay, but now let's narrow our focus a bit. From the entire universe down to our own familiar corner, the solar system.
Right, our neighborhood. And it's a pretty busy celestial neighborhood, wouldn't you say?
Absolutely. And what a vibrant neighborhood it is. At its very heart, you've got our sun, the only star in our system, anchoring everything. Then it's orbited by the 8 primary planets, plus several fascinating dwarf planets like Pluto, Ceres, Eris, Haumea, Makemake.
Right, the dwarf planets.
And then there's just a whole lot of what you might call cosmic leftovers from its formation. Asteroids, meteoroids, comets, and loads of natural satellites and moons.
Okay, so how did this whole system come about? What's the leading idea?
Well, the leading scientific explanation is the nebular theory. It was first proposed by Immanuel Kant way back in 1755 and later refined by Laplace.
Okay.
It suggests the solar system started as a nebula, a massive rotating cloud of dust and gas, mostly hydrogen and helium, just this huge cloud of raw primordial material.
And from that enormous cloud, the sun basically ignited.
Exactly, through an amazing process, nuclear fusion. Imagine hydrogen atoms in the core fusing together to create helium, releasing an incredible amount of energy. That fusion reaction is why the sun is the absolute powerhouse of the solar system. It's mostly hydrogen and helium, and it holds something like 99% of our solar system's entire mass. It's almost everything.
That's incredible. And this all happened when?
This whole formation process for both our sun and the planets orbiting it unfolded roughly 4.5 billion years ago.
Ah.
So it's a truly ancient system.
Okay. And speaking of light and power, it's probably worth clarifying the difference between luminous and non-luminous bodies in space.
Good point. So you have luminous bodies like stars, which generate and emit their own light.
Right.
But then there are unluminous bodies like our moon, which don't glow on their own. They just reflect light from other sources like our sun. It's a key concept for understanding what we actually see up there.
Absolutely fundamental. And thinking about our sun specifically, there are some really captivating facts that highlight its immense power and scale.
Oh, yeah.
It's about 150 million kilometers from Earth. Its light takes roughly 8 minutes and 30 seconds to reach us, traveling at, well, an incredible 300,000 kilometers per second.
That's light speed.
Exactly. And while its surface is around 5,600 degrees Celsius, its core is an unimaginable 15.7 billion Kelvin.
Just mind-blowing temperatures. And it's not just theory. Our quest for solar knowledge is very active. India's first solar mission, ADWAY L1, launched by ISR,
Right.
is a perfect example of our ongoing scientific exploration of this incredible star.
It's a fantastic example. And because these distances in space are just so immense, astronomers use special units, right? Like light years.
Exactly. A light year is the distance light travels in 1 year, about 9.46 trillion kilometers. It's huge.
Wow.
And even bigger is a parsec, which is 3.26 light years. These units really just emphasize the unimaginable scale we're dealing with.
And our sun, of course, isn't the only star out there. Stars are these luminous bodies, and their color actually tells us about their temperature, doesn't it?
It does. Hotter stars tend to look bluer, while cooler ones are redder.
And we group them into patterns, constellations like Orion or Ursa Major, the Big Dipper.
Right, or Saturishi in India. And while Rigel is the brightest star in Orion, the brightest star in our entire night sky is Sirius, the dog star.
Okay. And just to be clear, the sun is our closest star, obviously, but the next closest after the sun is Proxima Centauri.
Correct. Still incredibly far away, though.
Okay, we've zoomed out to the universe, zoomed in on our star. Now let's take that guided tour of our immediate celestial neighborhood. The planets. We usually group them into two main categories, right?
That's right. We start with the inner or terrestrial planets. These are the rocky, denser worlds closest to the sun.
Mercury, Venus, Earth, and Mars.
Exactly. And a big feature of this inner zone is the asteroid belt, that huge ring of rocky bits, basically leftover planetary building blocks sitting between Mars and Jupiter. There's a theory, the planetesimal hypothesis from the early 20th century, that suggests these planets formed from the gradual buildup of these smaller bodies, these planetesimals.
Interesting. Let's start with Mercury then, the swift messenger. Closest to the sun, smallest planet.
Right. And it lives up to its name, orbits in just 88 Earth days. Fastest revolution period.
But what's really striking is no satellites, no water, almost no atmosphere.
Exactly. Which leads to what's called the greatest diurnal temperature in the solar system.
Okay, what does that actually mean, that extreme temperature swing? What does it imply for any environment there?
It means a massive difference between day and night temperatures. Without an atmosphere to hold or spread the heat,
Right.
the side facing the sun gets incredibly hot, over 400 degrees Celsius, but the night side plunges down to maybe minus 170 Celsius.
Wow, that's extreme.
Totally. It makes any kind of stable environment for life as we know it pretty much impossible. Really shows how crucial Earth's atmosphere is.
Then we get to Venus, often called Earth's fiery twin, or even Lucifer.
Yeah, light bearer, because it's so bright. Surprisingly, it's the hottest planet, even though Mercury is closer.
Why is that?
It's because of a runaway greenhouse effect. It has this incredibly thick atmosphere, packed with trapped gases, mostly CO2, and clouds of sulfuric acid.
Nasty stuff.
Yeah. It's the brightest planet. You see it as the evening star or morning star. No moons, like Mercury.
And why Earth's twin?
Similar mass and size. But here's the weird part. Venus rotates clockwise, opposite to most planets.
Well, right, like Uranus.
Exactly. And it rotates incredibly slowly. It takes 243 Earth days for one rotation. So a day on Venus is actually longer than its year.
That is bizarre. What could cause that?
It's a puzzle. Could be something about its formation, or maybe a massive impact in its past. It just shows how different planets can end up, even if they start out similar in size.
And then our home, Earth, the blue oasis.
Yep, the only place we know of that supports life, called Blue Planet, because what, 70% is covered by water?
That's right. And it's also the densest planet in the whole solar system. And of course, we have our one companion, the moon.
Our unique spot in the habitable zone, liquid water, stable atmosphere. It really is a cosmic gem.
Okay, next stop. Mars, the red enigma.
Called the red planet because of all the iron oxide, basically rust, in its soil. It's the second smallest planet. Has two little moons, Phobos and Deimos.
What really stands out to me about Mars is Olympus Mons.
Ah, yes, the giant
The
volcano.
largest volcano and the tallest mountain in the entire solar system. That just screams, a really active geological past, doesn't it?
It absolutely does. Olympus Mons is a shield volcano, which suggests huge, slow lava flows over millions of years. It hints that Mars might have been a much more dynamic, maybe even wetter world long ago.
Fascinating. Okay, moving outward from the rocky inner planets.
We hit the outer, or Jovian, planets, the gas giants.
Huge spheres, mostly gas, much less dense.
Right. And beyond Neptune, the edge of the main system, you have the Kuiper Belt, this huge icy region full of dwarf planets like Pluto, asteroids, comets. Think of it as a big outer ring of leftover stuff.
Okay, first giant, Jupiter, the king of the planets.
Definitely the giant. Largest planet, and it spins the fastest a day is less than 10 hours, just 9 hours, 56 minutes precisely. Yeah. Its atmosphere is this swirling mix of hydrogen, helium, other gases. Third brightest thing in the night sky after the moon and Venus.
And it has the most moons, right?
Holds the record. 92 confirmed moons last time I checked. The four biggest Io, Europa, Ganymede, which is the largest moon in the whole solar system.
Bigger than Mercury.
Yeah. And Callisto, all discovered by Galileo. Jupiter also has faint rings, though they're hard to see.
But why is it sometimes called the winter planet?
Mostly because it's so far from the sun and so huge, it gets much less solar heat than we do. A lot of its internal heat actually comes from its own slow gravitational compression.
Ah, okay.
Plus, its massive gravity really affects everything else around it, like a cosmic gatekeeper. It's a seriously big, cold world out there.
Then there's Saturn, the ringed jewel. Just beautiful.
Iconic, isn't it? Second largest planet, famous for those bright concentric rings. They're made of countless bits of rock, dust, gas, and ice.
And here's a fun fact. It's the least dense planet, so light, it would float in water.
If you could find a big enough bathtub, yeah. And it also has a ton of moons, maybe 146 now. Its largest is Titan.
And people discover its features over time.
Right. Huygens saw the rings first in 1655. Then Cassini found the gap between the rings, the Cassini divisions, in 1675.
And some of its moons, like Titan and Enceladus, they show signs of maybe having life.
Yeah, that's incredibly exciting. Evidence suggests they might have subsurface oceans of liquid water. Could there be microbes down there? It really makes you wonder what else is hidden in our own solar system.
Definitely. Next, Uranus, the green ice giant.
Gets its greenish color from methane in its atmosphere, the green planet. Discovered by William Herschel in 1781.
An ice giant, like Neptune. Atmosphere of hydrogen, helium, water, ammonia, methane. And like Venus, it rotates clockwise.
That's right, and it's the coldest planet. But the really weird thing is its tilt.
Oh yeah, the 98 degrees.
Exactly. It's tilted way over on its axis, so it looks like it's rolling around the sun on its side. They call it the rolling or lopsided planet.
That must make for some crazy seasons.
Extremely long and strange seasons, yeah. One pole gets decades of sunlight, the other decades of darkness. It's unique.
And then Neptune, the distant ice giant.
Farthest planet now. Also an ice giant with a bluish color from methane. Fourth largest. Third most massive.
And it was found by math first.
Yeah, uniquely. It was discovered through mathematical predictions before anyone actually saw it. Johann Galli and Urbain Le Verrier pinpointed it in 1846.
Amazing.
He has 14 moons, Triton being the most famous, and its orbit takes the longest 165 Earth years.
Wow. It's just incredible how much we've learned, but also how much is still out there, how our understanding keeps changing.
Absolutely. And that includes big changes, like the reclassification of Pluto.
Right, from planet to dwarf planet. Why did that happen?
So in 2006, the International Astronomical Union, the IAU, set out new criteria for what makes a planet.
Okay, what are they?
3 things. 1, it has to orbit the sun. 2, it needs enough gravity to pull itself into a nearly spherical shape.
Pluto does those.
Right. But 3, and this is the key one, it must have cleared the neighborhood around its orbit, meaning it has to be the gravitationally dominant object in its path, having swept up or flung away most other smaller bodies.
Ah, and Pluto hasn't done that.
Exactly. It shares its orbital space with lots of other objects in the Kuiper Belt. So even though it's the largest and brightest dwarf planet, it didn't meet that third rule.
Got it. Its largest moon is Charon, and its year is 248 Earth years long.
A very long trip around the sun.
And Pluto isn't the only dwarf planet. There's Eris, Makemake, Ceres in the asteroid belt, Haumea.
Right. And beyond these, we have other cosmic events. A supernova, the explosion of a star, a pulsar, a spinning neutron star, and black holes with that immense gravity. The universe is full of dramatic stuff.
Let's bring it a bit closer home again. Earth's moon, our constant companion.
Our natural satellite. And as we said, non-luminous, it just reflects sunlight.
Its radius is about 740 kilometers, orbits around 384,000 kilometers away, and its light takes just over a second to reach us, 1.26 seconds.
And its gravity is much weaker than Earth's, only about 1/6. That's why astronauts bounced around up there.
Right.
That lower gravity is also key for its interaction with Earth, especially with tides.
And then there's its motion. It spins at the same rate it orbits us.
Exactly, synchronous motion. Its rotation takes about 27.3 days, and its revolution around Earth also takes 27.3 days.
Which is why we only ever see one side of the moon from Earth, the near side.
Pretty much. Though over time, due to wobbles, we actually get to see about 60% of the near side, but never the far side directly from Earth. It's called tidal locking.
And lunar exploration is still going strong. India's Chandrayaan-3 mission.
Yeah, a great success. With the Vikram lander and the Pragyan rover, they even named the landing spot Shiv Shakti Point. It shows we're still actively exploring our closest neighbor.
Okay, from the moon stands, let's look at Earth's own movements. Rotation and revolution, the rhythm of our planet.
Let's start with rotation, our daily spin.
Earth spinning on its axis, west to east, anti-clockwise.
Right, and most planets do that. But remember, Venus and Uranus spin clockwise. The rebels.
And it's not exactly 24 hours, is it?
No, it's precisely 23 hours, 56 minutes, and 40.91 seconds.
And the speed varies. Faster at the equator.
Much faster. About 1,667 kilometers per hour at the equator, decreasing down to basically 0 at the poles. And this spin has huge consequences.
Like days and nights, obviously.
The most fundamental one, yeah. But also time zones, that difference of 1 hour for every 15 degrees of longitude. And it deflects winds and ocean currents. That's the Coriolis force we'll talk more about. It even plays a role in tides.
And because of Earth's tilt and rotation, we get variations in daylight?
Exactly. Longest day in the Northern Hemisphere around June 21st, the summer solstice. Shortest day around December 22nd, winter solstice. Opposite in the Southern Hemisphere.
But at the equator, days and nights are pretty much equal all year round.
Roughly equal, yeah.
Okay, now revolution. Our annual trip around the sun.
The orbit itself, an object's motion around another object. And Earth's path isn't a perfect circle, it's an ellipse.
Meaning sometimes we're closer, sometimes farther away.
Right. The farthest point is called aphelion. That happens around July 4th, when we're about 152 million kilometers from the sun.
And just to remind everyone about Earth's shape.
It's an oblate spheroid, or oblate ellipsoid. Basically, almost spherical, but slightly flattened at the poles and bulging a bit at the equator, thanks to the spin.
Got it. Lastly in this section, eclipses. Lunar and solar. These amazing alignments.
A lunar eclipse happens only on a full moon day. Earth passes between the sun and moon, casting a shadow on the moon.
But why doesn't it happen every full moon?
Good question. It's because the moon's orbit is tilted slightly, about 5 degrees, relative to Earth's orbit around the sun.
Ah, so the alignment isn't usually perfect.
Exactly. Most months, the moon passes just above or below Earth's shadow. During an eclipse, the moon often looks red.
The blood moon.
Right. That's because Earth's atmosphere scatters the blue light, but lets the red light bend through and hit the moon.
Cool. And a solar eclipse.
That's when the moon passes directly between the sun and Earth, blocking the sun's light, either fully or partially. This can only happen during the new moon phase.
Often more dramatic, turning day into a kind of twilight.
It's a truly spectacular sight when the alignment is just right.
Okay, we've done the cosmos, our solar system, Earth's movements. Now let's get grounded, literally. We're going to peer beneath our feet into Earth's interior. But how do we even know what's down there? We can't just, dig a hole to the center.
No, definitely not. That's the big challenge. Direct observation is incredibly difficult. Our deepest drills have barely scratched the surface, relatively speaking.
So what do we do?
We rely heavily on indirect clues, and some limited direct ones. Indirect sources are key, like studying how temperature increases with depth tells us about heat flowing from the core.
Okay.
Analyzing meteorites leftovers from the solar system's formation gives us hints about the composition of planetary building blocks, including ours.
And direct sources.
Limited, but useful. Things like volcanic eruptions bring up material from deep inside. Rocks that have been pushed up from deep down also give us clues.
All right, let's unpack the layers then, starting with the outermost one, the crust,
Yeah.
the part we live on.
Right. It's surprisingly thin compared to the whole planet. Thickness varies, maybe 5 kilometers under the oceans, up to 70 kilometers under big mountain ranges.
And it's mostly made of lighter stuff, silica and aluminium, Cl.
Primarily, yes.
There.
And there are two main types of crust. Continental crust, thicker, maybe 30 kilometers on average, lighter, mostly granitic rock.
Like the continents themselves.
Exactly. And then oceanic crust, much thinner, only about 5 kilometers, but denser, made of basaltic rock.
Okay. And element-wise, the whole crust is mostly oxygen.
Oxygen is number one, about 36%, then silicon at 28%, and aluminium at 8%, which makes it the most abundant metal in the crust.
Which probably explains why we use aluminum for so many things. Cans, planes.
Its abundance, yeah, combined with being light and strong and resisting corrosion once it's processed. Our geology directly impacts the resources we use.
Makes sense. Okay. Beneath the crust.
We have the mantle. This thick, dense layer of rocky stuff goes down almost halfway to the center, about 2,900 kilometers deep.
A composition.
Mostly silica and magnesium, sema. The very top part of the mantle is solid rock.
And we divide it into upper and lower mantle.
We do. But the really critical part, especially for understanding why the surface moves, is a zone within the upper mantle called the asthenosphere.
The semi-molten or plastic layer. Why is that state so important?
It's absolutely vital. Think of it as a very slow-moving, super viscous fluid, like really thick honey or tar. It allows the rigid plates above it, the lithosphere, which is the crust in that solid upper mantle bit, to actually float and move around slowly.
Ah, so that's what enables plate tectonics.
Precisely. Without the flowing asthenosphere, no plate movement, no earthquakes, no volcanoes, no big mountain ranges formed by collisions. It's the engine driving all that surface activity.
Wow. Okay, and at the very center.
The core, made mainly of nickel and iron knife.
Also in two parts.
Yep. A solid inner core, about 2,200 kilometers thick, surrounded by a liquid outer core, about 1,300 kilometers thick.
And the liquid outer core has magnetic properties. What's the significance of that?
It's hugely significant. Life-saving, actually. That churning, convecting liquid iron generates Earth's powerful magnetic field.
The one that protects us.
Exactly. It acts like an invisible shield, deflecting most of the harmful solar wind and cosmic rays that stream from space. Without it, that radiation would strip away our atmosphere and bombard the surface. Life as we know it wouldn't be possible.
So the core is our planetary guardian. Amazing.
It really is.
Moving through these layers, scientists identified boundaries, right? Discontinuities.
Yes, these are transitional zones where the physical properties of the rock change abruptly, like density or the speed seismic waves travel through them.
And they found these by studying earthquake waves.
Primarily, yes. Changes in wave speed revealed these boundaries. The most famous is the Mohorovicic discontinuity, or MOHO for short. That's the boundary between the crust and the mantle, around 100 kilometers down.
Okay. Any others?
Yeah, several. Deeper down, the Gutenberg discontinuity separates the mantle and the core. And the Lehman discontinuity marks the boundary between the liquid outer core and the solid inner core, way down at about 5,200 kilometers. Mapping these helps us model the Earth's interior.
And just to clarify, the lithosphere versus asthenosphere again.
Right. Lithosphere is the rigid outer shell crust plus the solid upper part of the mantle, maybe 10 to 200 kilometers thick.
And the asthenosphere is below that, the weak flowing layer.
Exactly. The asthenosphere is not part of the lithosphere. It's the layer the lithosphere moves on.
Got it. And in terms of just how much stuff is in each layer, volume and mass.
It's quite revealing. The crust, the part we know best, is tiny, only about 1% of Earth's volume and 1% of its mass.
Really? Only 1%?
Yep. The mantle is the giant, about 84% of the volume and 68% of the mass.
Wow.
And the core, while only 15% of the volume, packs a punch. It's about 31% of the total mass.
What does that tell us about density?
It clearly shows density increases dramatically as you go deeper. The core must be made of incredibly dense material like iron and nickel to account for nearly a third of the mass in such a relatively small volume. That dense core gives Earth its overall mass and strong gravity.
Okay, from the structure, let's talk about movement and energy release. Earthquakes. That intense shaking.
Right. An earthquake is basically an intense shaking of Earth's surface. It happens when there's a sudden shift along a fault line in the Earth's plates. Built-up energy gets released, sending out waves in all directions.
And there are specific terms for the location.
Yes. The hypocenter, or focus, is the actual spot inside the Earth where the energy release begins, the origin point.
Okay.
The point on the surface directly above the focus is called the epicenter. And usually, the closer you are to the epicenter, the more destruction you'll see.
Makes sense. Now, the waves themselves. Seismic waves, two main types.
Correct. Body waves travel through the Earth's interior. Surface waves travel along the surface.
And surface waves cause more damage.
Generally, yes, because they travel along the ground we live on and can have larger amplitudes.
Okay, let's look at body waves first. P waves, primary waves.
Yep. They're the fastest, moving at 7-8 kilometers per second, so they're the first to reach the surface and be recorded by seismographs.
And they travel through anything, solid, liquid, gas.
They can, yes. Their speed changes depending on the material, which is actually how we learn about the interior.
Yeah.
They're like sound waves, pushing and pulling the rock compression and rarefaction.
Okay, and S waves, secondary waves.
Slower than P waves, maybe 4 to 6 kilometers a sec. And here's the crucial difference. They can travel only in solid medium. They shake the ground side to side or up and down, creating crests and troughs.
So if S waves can't go through liquid, what did that tell us?
That's how scientists figured out the outer core is liquid. There's a large shadow zone on the opposite side of the Earth from an earthquake where S waves are just not detected.
Because the liquid outer core blocks them.
Exactly. It covers about 40% of Earth's surface. P waves also have a shadow zone because they get refracted and slowed down by the liquid core. But S waves just stop dead. Yeah. It was brilliant detective work using seismic wave behavior.
Incredible. And sometimes underwater earthquakes trigger tsunamis.
Yes, powerful underwater quakes, volcanic eruptions, or landslides can displace huge amounts of water, creating these devastating long wavelength waves.
How do we measure earthquakes?
The instrument that records the waves is a seismograph. To measure the energy released at the source, the magnitude, we use the Richter scale. It's often shown as 0 to 10, but technically it's a limitless logarithmic scale.
Okay, and the shaking we feel, the damage.
That's measured by the Mercalli scale. It measures the intensity or the damage caused at a specific location using Roman numerals from I to 12, or sometimes I to added older versions. So Richter is source energy, Mercalli is observed effect.
Got it. Now let's tie this all together with plate tectonics, the Earth's moving puzzle pieces.
Right. Remember the lithosphere, that rigid outer layer of crust and solid upper mantle? It's not one solid piece. It's broken into these huge slabs called tectonic plates.
How many are there?
Geologists identify about 7 major plates and a number of minor plates. And these plates are constantly moving very slowly across the surface, floating on the asthenosphere.
And what happens where they meet? At the boundaries.
That's where the action is. When plates collide, often the denser one subducts, meaning it dives down beneath the less dense plate into the mantle.
And that causes
Earthquakes, volcanic activity, and the building of massive mountain ranges. Almost all major geological activity happens at these plate boundaries.
Yeah.
It's a constant reshaping process.
Which brings us neatly to volcanoes, Earth's fiery vents giving us a glimpse inside.
Exactly. Geologists classify them based on their shape, the kind of magma they erupt, and how explosive they are.
Okay, what are some types?
Well, you have basalt plateaus. These are the least explosive. They erupt very fluid, runny basaltic magma that flows out horizontally over huge areas.
Like floods of lava.
Kind of, yeah. They can build up deposits hundreds, even thousands of meters thick. Think of the Columbia River Plateau in the U.S. or parts of western India.
Then shield volcanoes, like in Hawaii.
Perfect example. They look like a warrior's shield, lying flat. Very large, slightly sloping volcanoes, maybe 6 to 12 degree slopes, formed by gently flowing magmas over long periods. They can get incredibly tall, up to 9,000 meters from the seafloor.
And smaller, more explosive ones.
Cinder cones. Relatively small, maybe 100 to 400 meters tall. They're basically made up of exploded rock blasted out of a central vent at high velocity. Often form when gas builds up in the magma. Paracutin in Mexico is a famous example that grew very quickly.
And many mountains are actually volcanic mountains.
Yes, they're literally built up from material ejected from fissures. Lava bombs, ash, dust. They're often called mountains of accumulation.
Where do we find most volcanoes?
They're very common along the Circum-Pacific Belt, the famous ring of fire around the Pacific Ocean.
That mnemonic again. Japan, USA can.
Right. Helps remember some key countries like Japan, USA, Canada, Indonesia, Philippines, Chile, all prone to earthquakes and volcanoes.
Specific examples. Mount Fuji in Japan.
Classic. Mount Mayon in the Philippines, Mount Merapi in Sumatra. Others like Vesuvius, Etna, Stromboli in Italy. Stromboli is called the lighthouse of the Mediterranean because it's almost constantly erupting.
India has one.
Barren Island in the Andaman and Nicobar Islands, it's active. And globally famous ones like Kilimanjaro in Tanzania, Krakatoa in Indonesia, Pinatubo in the Philippines. Izalco in El Salvador is the lighthouse of the Pacific.
Okay, from volcanoes to other major landforms, mountains, plateaus, plains, sculpted over time.
We've talked volcanic mountains. Let's cover fold mountains. These are the most common type, formed when crustal rocks get folded under stress.
Usually from plates colliding, compression.
Exactly. Powerful forces of compression often linked to earthquakes over millions of years. The Himalayas are a prime example, one of the youngest fold mountain ranges in the world, mostly made of folded sedimentary rocks that were once seabed.
And other examples.
The Alps, Andes, Rockies, Atlas Mountains, all major fold mountain ranges.
Okay, what about block mountains?
They form differently. When the crust is pulled apart by tensional forces, it can fracture, creating faults. If a block of land between faults stays up or is pushed up while the land on either side drops down,
It becomes a block mountain, a horst.
precisely. The Great African Rift Valley is a massive example, where the valley floor itself is a dropped block, a graben. The Rhine Valley and Vosges Mountains in Europe are other examples.
Then plateaus, elevated flat areas.
Elevated uplands with extensive level surfaces, yeah. They usually drop steeply to the surrounding lowlands. Can be formed by tectonic uplift or by massive volcanic flows building up. Two main types, tectonic and volcanic plateaus.
And plains, just flat areas.
Pretty much, flat areas of land. Can be in valleys, lowlands, even on plateaus or uplands. There are different types based on how they formed. Structural, erosional, depositional, like river plains, glacial, abyssal, on the deep ocean floor.
Understanding these helps see how the Earth's surface is constantly being shaped, and all these features are made of rocks and minerals.
The fundamental building blocks. And remember, about 98% of the crust is just 8 elements: oxygen, silicon, aluminum, iron, calcium, sodium, potassium, magnesium.
An amazing variety from such a limited palette. Okay, the 3 main rock types.
First, igneous rocks, fire-formed. They solidify from molten magma or lava as it cools.
And the cooling speed matters.
Critically, rapid cooling, like lava on the surface, means small crystals. Slow cooling, deep underground, allows large crystals to grow. Granite and basalt are classic examples.
And we divide them based on where they cool.
Right. Extrusive rocks solidify from lava on the surface. Basalt is common. Intrusive rocks form from magma that solidifies underground. Granite is a typical example.
Second type, sedimentary rocks.
These are made from sediments, bits of older rocks, sand, mud, organic matter that get deposited in layers, often underwater, and then compacted and cemented together over long periods. Sandstone, limestone, shale, coal, gypsum, conglomerate, lots of familiar ones.
And the third type, metamorphic rocks. Changed rocks.
Exactly. They start as any rock type, igneous, sedimentary, even other metamorphic rocks, and then get transformed by intense heat, pressure, or chemical reactions, usually deep within the Earth.
Takes millions of years.
Oh, yes. As rocks get buried deeper, the conditions change them fundamentally. What does this transformation tell us about Earth's processes?
Well, it shows how incredibly dynamic the Earth is, even deep down. The heat and pressure are immense enough to literally recrystallize and reshape existing rocks into totally new ones.
Perfect. Examples make it clear. Limestone turns into marble. Shale becomes slate. Granite morphs into gneiss. Sandstone transforms into quartzite. It's geology in action, constantly recycling and reshaping the planet's crust.
Okay, we've explored the solid Earth, inside and out. Now let's look up and around to Earth's protective blanket, the atmosphere.
This thick, gaseous envelope surrounding our planet, stretching thousands of kilometers out.
And it's not just there, it's vital for life, right?
Absolutely crucial. Much of the life on the Earth exists because of the atmosphere. Without it, Earth would be barren, like the moon.
Composition, mostly nitrogen and oxygen.
Yep, they make up 99% of the volume. But it's not uniform. The atmosphere has layers, almost concentric layers of air with varying density and temperature.
Let's go through them, starting at the bottom. The troposphere.
The lowest layer, where we live. And importantly, it's where all weather phenomena are confined. Fog, clouds, rain, storms, it all happens here.
How thick is it?
Varies. About 16 kilometers thick over the warm equator, thinner at the poles, maybe 10 kilometers, and temperature generally drops as you go higher.
The normal lapse rate.
Right. Roughly 6.5 degrees Celsius drop for every 1,000 meters you go up. Its upper boundary is the tropopause, a transition zone.
Above that stratosphere.
Correct. This layer is much calmer, more or less devoid of major weather phenomena. Maybe some thin cirrus clouds, feeble winds. That's why jets like to fly here. Perfect flying conditions.
And this is where the ozone layer is.
Critically, yes. Mostly between 15 and 35-kilometer altitude. It acts as our protective cover, absorbing most of the sun's harmful ultraviolet rays.
So ozone depletion is a big deal because...
It lets more UV reach the surface, which is harmful to life, and it can also affect temperatures.
And temperature in the stratosphere increases with height.
It does, unlike the troposphere. It goes from about -60 degrees C at the bottom up to near freezing at the top, the stratopause, because the ozone is absorbing that UV energy.
Okay, next layer up. Mesosphere.
Extends from about 50 to 90 kilometers. Here the temperature drops again, getting really cold, down to maybe -80 degrees C at the top, the mesopause.
And this is where meteors burn up, shooting stars.
Exactly. Friction with the air particles, even though they're sparse, heats them up intensely.
Above the mesosphere, thermosphere, also called the ionosphere.
Right, from about 80 kilometers up to maybe 640 kilometers, temperature shoots up rapidly here, getting extremely hot.
But it's also electrically charged. How does that happen, and why is it important?
Intense solar radiation knocks electrons off the gas atoms, creating ions. So it's an electrically charged layer. This is crucial for radio communication.
How so?
This ionized layer, with its sublayers, D, E, F layers, reflects radio waves transmitted from Earth back down to the surface. It allows long-distance radio signals to bounce around the planet. Without it, radio would be mostly line of sight.
Fascinating. And the very top layer?
The exosphere, the uppermost layer, extending out beyond the ionosphere. Very, very low density, extremely high temperatures, but you wouldn't feel it. It just gradually merges with outer space.
Okay, from the layers, let's talk about the forces driving air movement, pressure belts and winds.
First, basic air pressure. It's just the weight of the air column above a certain area at sea level, determined by temperature and density, measured as force per unit area.
And we measure it with a barometer, like an aneroid barometer.
Well, the common type, yes.
So Earth has these distinct pressure belts.
Yes, zones of generally high or low pressure that circle the globe. First, the equatorial low pressure belt, or the doldrums, around 5 degrees north and south of the equator.
Why is it low pressure there?
It's thermally induced. Intense heating causes air to rise, leaving lower pressure at the surface. This zone shifts a bit with the seasons.
And the subtropical highs? Horse latitudes. Around 30-35 degrees NNS.
Right, these are dynamically induced. Air that rose at the equator cools and sinks here, partly due to Earth's rotation and the Coriolis effect. Sinking air creates high pressure.
And high pressure often means?
Stable, dry conditions. Many of the world's great deserts are found under these belts.
Okay, then the temperate low pressure belts. Around 60-65 degrees NNS.
Also dynamically induced, where warmer air moving poleward meets cold polar air, forcing the warmer air to rise. More developed in the southern hemisphere because there's less land.
And finally, the polar highs.
High pressure right at the poles, mostly thermally induced because it's so incredibly cold, causing air to sink. Rotation plays a smaller role.
Now, that crucial force, Coriolis force. Earth's spin deflecting things.
Exactly. It's an apparent force caused by rotation. It deflects moving objects' wind, ocean currents to the right in the northern hemisphere and to the left in the southern hemisphere.
And it's strongest at the poles, weakest at the equator.
Zero at the equator, strongest at the poles. Its strength also increases with the speed of the object. How does this subtle force shape global patterns?
Well, it seems fundamental. Without it, wind would just go straight from high to low pressure. Coriolis is what makes wind systems spiral, like in hurricanes or cyclones.
Absolutely. And it drives the large-scale ocean circulation patterns, the gyres. It's responsible for redistributing heat and moisture all around the globe, fundamentally shaping climate everywhere. Think of trying to walk straight across a spinning carousel, you get deflected sideways. That's the Coriolis effect.
Great analogy. Okay, so winds themselves are just horizontal air movement.
Driven by pressure differences, always high to low. Speed depends on the pressure gradient, how steep the change in pressure is.
And we categorize winds, planetary winds first, global ones.
Right. These blow pretty consistently year-round due to the major pressure belts. Includes the trade winds, blowing from the subtropical highs towards the equatorial low, ITCZ. Northeast in NH, southeast in SH.
Westerlies in the mid-latitudes.
Yep, between roughly 35 and 65 degrees latitude. blowing from the subtropical highs towards the subpolar lows, generally southwest to northeast in NH, northwest to southeast in SH, stronger in winter and in the southern hemisphere where there's less land friction.
And polar winds, polar easterlies.
Blowing out from the polar highs towards the subpolar lows, generally northeast in NH, southeast in SH. Very cold, more regular in the south.
Second category, periodic winds, change direction.
Seasonally or daily. The big one is monsoon winds. Regional systems where the wind direction completely reverses with the seasons, driven by land-ocean temperature contrasts. We'll hit the Indian monsoon later.
Also land and sea breezes, daily things.
Yeah, along coasts. At night, land cools faster, air flows from land to sea, land breeze. During the day, land heats faster, air rises over land, cooler air flows in from the sea, sea breeze. Sea breezes are usually stronger.
Mountain and valley winds, too.
Similar idea. Daytime, mountainsides heat up, air rises up from the valley, valley breeze. Night reverses.
Third type, local winds, specific areas.
Right, often named. Can be warm, like the Sirocco from the Sahara carrying dust causes blood rain, or the Chinook in the U.S., the snow eater, Foehn in the Alps,
Or cold winds.
like the Mistral in France, Bora along the Adriatic coast, Pampero in Argentina, Buran in Siberia.
And finally, jet streams, high up, fast winds.
Way up in the upper troposphere, 9-14 kilometers. Bands of high-speed winds, maybe 95, 190 kilometers are average 120 in winter, 50 in summer. Polar jets and subtropical jets are the main ones, discovered formally around WWIL.
And they influence weather down here.
Massively. They steer weather systems like low-pressure storms. Where the jet stream goes often dictates where storms track and where you get big temperature changes. Crucial for forecasting.
Okay, from winds to bigger systems. Cyclones and anticyclones, swirling weather.
Cyclones are basically well-developed low-pressure systems. Air spirals inward towards the center. Closed isobars with pressure increasing outwards.
Direction of flow.
Anti-clockwise in the northern hemisphere, clockwise in the southern hemisphere.
And they bring bad weather.
Usually, yeah. Rising air leads to cloud formation, often big cumulonimbus clouds, causing heavy rain, thunderstorms, strong winds.
Two main types. Tropical cyclones.
Intense storms that form only over warm oceans of the tropics, extremely low pressure in the center, very high winds, over 34 knots or 39 miles per hour, can be incredibly devastating.
And they have different names depending on where they are.
Right. Cyclones in the Indian Ocean, hurricanes in the Atlantic, typhoons in the West Pacific South China Sea, willy-willies off Western Australia. Same phenomenon, different local name.
And temperate cyclones, extratropical.
These develop in the mid and high latitudes, outside the tropics, often form along the polar front, where cold polar air meets warmer tropical air.
How are they different from tropical ones?
Key differences. Tropical form only over warm seas. Temperate can form over land or sea. Tropical tend to be more intensely destructive, wind-wise, but less frequent. Temperate are less intense generally, but more frequent. Tropical usually move east to west. Temperate move west to east.
Okay. And anticyclones are the opposite.
Basically, high-pressure systems. Air flows outward from the center, clockwise in NH, anti-clockwise in SH, usually associated with stable, clear, calm weather.
And those global climate shifters, El Nino and La Nina.
Huge players. El Nino is that abnormal warming of sea surface temperature in the central and eastern equatorial Pacific.
And La Nina.
The opposite cooling of surface ocean waters in roughly the same region along the west coast of South America. What are their global impacts?
They mess with weather patterns worldwide, right? Rainfall, temperatures, storm tracks.
Totally. They act like a global climate switch. El Nino might bring drought to Australia and Indonesia, but floods to Peru. La Nina often does the reverse. They impact agriculture, fisheries, disaster frequency, huge economic and social consequences. Shows how connected the ocean and atmosphere are.
Definitely. Okay, let's dive into the vast oceans and their currents. The blue highways, 5 main oceans.
Yep. Pacific first, largest and deepest, covers over a third of the planet. Home to the Mariana Trench, the deepest spot, almost 11,000 meters down.
Unimaginable pressure down there.
Makes you wonder about life under extreme conditions. Then the Atlantic, second largest, that distinctive S-shaped basin, busiest for trade. Lowest point is the Puerto Rico Trench. Panama Canal connects it to the Pacific.
Indian Ocean, third largest.
And unique, the only ocean named after a country. Deepest point is the Java Trench. Critically important for trade with choke points like the Suez Canal, Strait of Hormuz, Strait of Malacca.
Southern Ocean, around Antarctica.
Fifth largest, encircling Antarctica, sometimes called the Antarctic Ocean.
And the smallest, Arctic Ocean.
Smallest, shallowest, coldest. mostly north of the Arctic Circle. Important shipping routes like the Northwest Passage and Northern Sea Route are opening up more as ice melts. Deepest point is the Nansen Basin.
Okay, beneath the waves, the ocean floor has divisions.
Hidden landscapes, yeah. Starts with the continental shelf, shallowest part, right off the coast, usually less than 200 meters deep, covers about 7.5% of the ocean area. Why is this zone so useful to us?
Fishing, oiling bass.
Exactly. Most marine food comes from here. About 20% of world oil and gas. Sunlight penetrates, supporting lots of life, making them incredibly productive fishing grounds.
Then it drops off the continental slope.
Steep drop-off from the shelf edge down to deeper water, maybe 200 to 2,000 meters or more, covers about 8.5% of the ocean floor, often cut by deep submarine canyons.
And at the bottom of the slope?
The continental rise, a gentler slope where sediments accumulate, transitioning to the deep ocean basin.
The deep ocean basins themselves, what's down there?
Vast areas. You find deep ocean trenches, long, narrow, the absolute deepest parts. Most are in the Pacific, like the Mariana.
Abyssal plains. Super flat.
Incredibly flat. Most level places on Earth. Less than 3 meters of relief over huge distances, like 1,300 kilometers. Covered in thick sediment that buries the underlying rocky floor.
Seamounts. Underwater volcanoes.
Isolated volcanic peaks rising at least 1,000 meters from the ocean floor. Many in the Pacific formed near ridges. Some break the surface as islands.
And submarine canyons.
V-shaped valleys carved into the slope and sometimes the shelf, often by underwater landslides or turbidity currents. Can be quite large.
Now, ocean currents. Moving water masses.
Large masses of surface water circulating in regular patterns. We classify them as warm currents, flow from equator polewards, higher temp, and cold currents, flow from poles equatorwards, lower temp.
What makes them move?
Several factors. Sun's heating, wind pushing the surface, density differences. Colder, saltier water is denser and sinks. Coriolis force deflecting them, and the shape of coastlines blocking or redirecting flow.
2 types, surface and deep sea.
Right. Surface currents are about the top 10% of ocean water, mostly wind-driven. Deep sea currents are the other 90%, driven by density differences, thermohaline circulation. Generally, cold water moves towards the equator deep down, warm water moves towards the poles at the surface.
And they have big effects, like fishing zones.
Huge effects. Where warm and cold currents meet, like the cold Labrador current meeting the warm Gulf Stream off Newfoundland, you get mixing, lots of nutrients, and therefore best fishing zones.
Why does that happen?
The mixing brings nutrients from the deep cold water up to the sunlit surface, feeding plankton, which feeds fish. It creates a really rich ecosystem.
Then cold currents have other effects, like creating deserts.
Yes. Cold water cools the air above it, making it stable and less likely to form rain clouds. That's why many deserts are on the west coast of continents next to cold currents. They also cause fog when warm, moist air blows over them. Bad for shipping.
Can we trace some major currents? Atlantic?
Sure. South equatorial current splits into the Cayenne and Brazil currents. Florida current flows into the powerful Gulf Stream, which gets deflected by westerlies in rotation, becoming the North Atlantic drift warming Europe. Cold Labrador current meets the Gulf Stream. Cold Benguela current off Africa corresponds to the Canaries current off Europe-Africa.
Pacific.
North equatorial current driven by trades becomes the warm Kuroshio-Japan current. Cold Ayashio current meets it. South equatorial current becomes the East Australian current, then loops back as the cold Humboldt-Peruvian current along South America's west coast.
Indian Ocean, unique reversal.
Yes, in the North Indian Ocean. The currents completely reverse direction between summer and winter because of the changing monsoon winds. Southwest monsoon drift in summer, northeast monsoon drift in winter. Shows how dominant winds can be.
Finally, tides. The ocean's rhythmic pulse, caused by gravity.
Primarily, yes. The periodic rise and fall of sea level caused by the combined gravitational pull of the moon and sun, plus Earth's rotation. Who's mainly responsible?
The moon, right, because it's closer.
Exactly. The moon is mainly responsible for the tides. Its gravity has a stronger effect than the sun's, even though the sun is much bigger.
And usually 2 high and 2 low tides a day, semi-diurnal.
Most places, yes. Recurring every 12 hours and 25 minutes or so. Some places have only 1 high and 1 low per day, diurnal tide, about 24 hours, 50 minutes apart.
What influences the timing and height?
The alignment of sun and moon, ocean depth, coastline shape, underwater topography, it's complex locally.
2 main types, spring tides and neap tides.
Right. Spring tides are the especially strong tides, higher highs, lower lows. They happen when Earth, sun, and moon are in a line. At new moon and full moon, their gravity adds up.
And neap tides, weaker.
especially weak tides. Less difference between high and low. Happen when the sun and moon are perpendicular to one another relative to Earth at quarter moons. Their gravitational pulls partially cancel each other out.
Also monthly tides, based on moon's distance.
Yeah, tides are slightly stronger when the moon is at perigee, closest to Earth, and weaker at apogee, farthest.
Any extreme examples?
The Bay of Fundy in Canada, between Nova Scotia and New Brunswick, has the world's greatest tidal range, up to 50 feet or 15.25 meters. Just a massive difference between high and low tide.
Okay, we've covered the big global picture. Now let's zoom right back in, focus on the geography of India. It's such a land of incredible extremes and diversity.
It truly is. Let's start with the mountains of India, especially the northern ramparts, the Himalayas.
The abode of snow?
Right, one of the youngest fold mountain ranges in the world, remember, formed by crustal compression, mainly sedimentary rocks. They stretch from the Indus River in the west, clear across to the Brahmaputra in the east. A massive natural barrier.
And they're divided into zones?
Usually into 3 parallel zones running lengthwise. And in the east, you have the eastern Himalayas or Provençal ranges like the Patkai Hills, Naga Hills, Mizo Hills.
And connecting the Himalayas to Central Asia.
The Pamir Knot, known as the roof of the world. It's where several major ranges converge, a key geographical hub.
South of the mountains, the plains of India, vast, fertile.
The Great Plains of North India, formed by the sediments deposited by 3 huge river systems, Indus, Ganga, and Brahmaputra.
Alluvial plains, meaning fertile soil.
Extremely fertile alluvial soil, sand, silt, clay. The western part is the Thar Desert, but the rest is incredibly productive. The alluvium is thickest in the Ganga Plains.
And there are divisions within the plains, Habar, Tarai.
Yes. Habar is the poorest gravelly zone right at the foothills where streams disappear. Tarai is south of that, marshy, where streams reemerge. Bongar is the older alluvium, sometimes with lime nodules, called Kankar. Kedar is the newer alluvium on the active floodplains, also called betlands, very fertile.
And delta plains at the river mouths.
An extension of the Kedar, basically. Mud and marsh.
South of the plains, the peninsular plateau, ancient heartland.
The old stable block, spread south of the Indo-Gangetic Plains Sea on 3 sides, shaped like a triangle with its base in the north, flanked by the Eastern Ghats and Western Ghats.
And the Narmada River divides it.
Yes, flowing through a rift valley, it splits the region into the Malwa Plateau in the north and the large Deccan Plateau in the south. There are other plateaus, too, like the Vindhya and Chota Nagpur plateaus.
This landscape shapes the rivers of India, the lifelines. 2 main groups.
Himalayan rivers and peninsular rivers.
Himalayan rivers start from glaciers, perennial.
Yes, fed by glaciers and snowmelt, so they flow year-round. The Indus system rises in Tibet, flows through India, joined by major tributaries like Halem, Chenab, Ravi, Beas, Satluj. Total length, 2,880 kilometers, 709 kilometers in India.
The Ganga system.
Longest in India.
225 kilometers long within India. Headstream formed by Bhagirathi and Alaknanda joining at Devprayag. Hugely important culturally, India's sacred river, but also facing pollution challenges, unfortunately listed as one of the most polluted.
And the Brahmaputra system, the Red River.
Also originates in Tibet. Navigable for a long stretch in India, an excellent inland water transport route.
Now, peninsular rivers, mostly rain-fed, older. Generally, yes. Divided into east-flowing and west-flowing. East-flowing rivers mostly go to the Bay of Bengal and form deltas.
Like the Mahanadi with the Hirakud Dam.
Right. World's longest dam is on the Mahanadi. Godavari is the longest peninsular river, 1,365 kilometers, called Dakshina Ganga. Rises near Nasik.
Krishna River.
Rises near Mahabaleshwar. Important tributaries like Bhima, Tungabhadra. Nagarjuna's Sagar project is on it.
Kaveri River flows year-round.
Uniquely, yes, almost throughout the year due to getting rain from both southwest and northeast monsoons. Largest peninsular river by water volume. Rises in the Western Ghats. Shivasamudram project, India's oldest river valley project, is on the Kaveri.
Okay, west-flowing rivers go to the Arabian Sea, form estuaries, not deltas.
Generally, yes. Because the Western Ghats are steep and rocky, the rivers don't have wide floodplains near the coast to deposit sediment and build deltas. The hard rocks don't allow western-flowing rivers to widen their mouth into sea.
Narmada River, longest estuary former.
Yes, 1,312 kilometers. Rises in a Markantak Plateau, flows through that rift valley into the Gulf of Combat. Famous Tuandar falls near Jabalpur. Major projects like Indira Sagar Lake, largest man-made lake in India, and Sardar Sarovar.
Tapti River, Narmada's twin.
Also flows west from Maharashtra. known as the twin or handmaid of Narmada.
Luni River, the salt river, disappears.
Rises in the air valleys, flows for a bit, but then gets lost in the marshy grounds at the head of the Ren of Kutch. Doesn't reach the sea.
Interesting. What about lakes and gulfs?
Important water bodies. Largest brackish water lake, Chilka Lake in Orissa. Also the largest lake of India overall.
Largest freshwater lake.
Uller Lake in Jammu and Kashmir. Other famous ones. Dal Lake, J&K. Vembanad, Kerala. Kolaroo and Pilakkat, Andhra Pradesh.
Salt production from lakes.
Samvar and Didwana lakes in Rajasthan are key sources.
And gulfs in Indian territory.
Gulf of Kutch, West Gujarat, noted for highest potential of tidal energy generation. Gulf of Kambakamba, Gujarat, or Narmada, Tapti, Mahi, Sabarmati drain. Gulf of Mannar, southeast Tamil Nadu, Asia's first marine biosphere reserve.
Okay, shifting to India's climate. Tropical monsoon type.
Yes, dominated by the tropical monsoon type of climate.
And the seasons are driven by the monsoons, differential heating.
Exactly. India's 4 main seasons result from the monsoons, which occur mainly due to the differential heating of land and movement of the sun's vertical rays. Hottest temps hit South India in April, North India in May, June.
Pre-monsoon showers have names. Cherry blossoms, mango showers.
Yeah, localized names for showers that happen before the main monsoon arrives, often beneficial for specific crops like coffee or mangoes.
The main monsoon, southwest monsoon, enters in 2 branches.
Bay of Bengal branch and Arabian Sea branch. Causes rainfall over most of the country except parts of Tamil Nadu and the Thar Desert.
And that extreme rainfall in Masinram, Bay of Bengal branch.
Yes, that branch hits the Khasi Hills in Meghalaya. The funnel shape traps the moist air, forcing it to rise rapidly, leading to perpendicular strikes on Cherrapunji and Masinram, causing the heaviest rainfall, around 1,400 centimeters, making Masinram the wettest place on Earth.
Incredible. Then the northeast monsoon, retreating monsoon.
Occurs from mid-September to mid-December. Sun moves south, low pressure shifts, winds reverse, blowing from land to sea. Withdrawal is a much more gradual process than its onset.
And this brings rain to Tamil Nadu.
Yes. As the winds blow back across the Bay of Bengal, they pick up moisture and drop it on the Tamil Nadu coast. This explains why Tamil Nadu is often dry during the SW monsoon and wet during the NE monsoon, the opposite of most of India.
Fascinating pattern. India also has diverse climatic regions based on Köppen's system.
Yes. Köppen's classification uses temperature and precipitation to define different zones. India has a wide range. Tropical rainy on the west coast, tropical savanna over much of the peninsula, semi-arid steppe in rain shadow areas, tropical desert in the far west, humid subtropical in the north, and distinct mountain climates in the Himalayas.
What factors affect India's overall climate? Latitude is key.
Definitely. Tropic of Cancer cuts right through, making half tropical, half subtropical.
Altitude, the Himalayas.
Huge impact. Average elevation varies greatly. But crucially, the Himalayas block frigid winds from Central Asia, giving India comparatively milder winters than other places at the same latitude.
And pressure and winds, the monsoon drivers.
Yes, India lies in the path of winds influenced by the subtropical highs and the seasonal shifts in pressure over the landmass and ocean, driving the monsoon circulation. Coriolis deflects these winds too.
Okay, climate determines soils and natural vegetation. Let's look at India's soils.
Alluvial soil is dominant, about 40% of the land. Very fertile, crucial for agriculture. Found in the northern plains and coastal areas, remember Bangar, Old, and Kadar, New. Great for rice, wheat, sugarcane, cotton.
Black soil, Ragar, good for cotton.
Yes, black cotton soil. Found mostly in the Deccan Trap area, Maharashtra, Gujarat, MP. Famous for holding moisture well, good for cotton, wheat, oilseeds.
Red soil, covers a lot of the peninsula.
But at 18%. SE Peninsular India, Tamil Nadu, Karnataka, etc. Red color from iron oxide, rich in potash, but needs management as it can be poor in other nutrients like nitrogen and phosphorus.
Laterite soil, found in high rainfall areas, leached.
Derived from Latin for brick. Found on hill summits, western eastern Ghats, etc., where heavy rain causes leaching, washing away fertile elements. Reddish gravelly, generally not very fertile on its own, but good for plantation crops like tea, coffee, rubber, coconut, if managed well with manure and irrigation.
Mountain soil, varies with altitude.
Found on forest-covered hills. Rich in humus, but often poor in potash phosphorus. Supports different crops depending on altitude. Temperate fruits higher up. Tea, coffee, spices in the southern hills.
Desert soil, arid regions, sandy.
Rajasthan, parts of Haryana, Punjab, Ran of Kutch. Less than 50 centimeters rain, mostly sand, 90–95%. Can grow hardy crops like millet, barley, some cotton with irrigation.
Now, natural vegetation, forest type.
Tropical evergreen forests, high rainfall areas, 250 centimeters like Western Ghats, India, Andamans, dense, multi-layered, rosewood, ebony.
Tropical deciduous forests, most widespread, shed leaves.
Areas with 100–200 centimeter rain, peninsula region, Himalayan foothills. Trees drop leaves in dry seasons, spring, early summer, to save water. Teak, sal, bamboo, sandalwood.
Tropical thorny forests, dry areas.
Low rainfall, 25–80 centimeters. Arid parts of Rajasthan, Punjab, Gujarat, acacias, palms.
Alpine, subalpine forests in the mountains.
Himalayas and southern hills. Vegetation changes drastically with altitude. Saw bamboo low down, oaks, chestnuts higher, pine deodar higher still, then alpine forests, firs, birches, and finally grasslands above 3,600 meters.
Tidal or mangrove forests, coasts and estuaries, sunderbans.
Also called littoral swamp forests, adapted to salty, waterlogged conditions. Sunderbans is the largest. Sundari tree is important, yields hard timber for boats. Construction.
Quick forest facts. Largest forest area state.
Madhya Pradesh, followed by Arunachal Pradesh.
Highest percentage of forest area.
Andaman Nicobar Islands, UT, followed by Mizoram State.
Lowest forest percentage.
Haryana and Punjab, due to intensive agriculture.
Mangrove forests leader.
West Bengal, Sundarbans. Then Gujarat, then Andaman and Nicobar.
Okay, crucial topic. Conservation and agricultural innovations in India. Protecting resources and boosting food output.
Conservation efforts include biosphere reserves. First was Nilgiri, 1986. Now 18 across India. Protect large ecosystems.
National parks and wildlife
A
sanctuaries.
large network. 103 national parks, 544 wildlife sanctuaries currently. MP and Andamans have the most national parks, 9 each. Andamans have the most wildlife sanctuaries, 96, followed by Maharashtra, 42.
Famous examples. Gur, Asiatic lion. Kaziranga, rhino. Corbett, Sundarbans, tiger.
Bandipur, Periyar, Kanha. Many vital protected areas.
Now, agriculture. Cropping seasons. Kharif, Rabi, Zaid.
Kharif or summer monsoon crops. Sown May, July, harvested Sept–Octo. Rice, maize, cotton, sugarcane.
Rabi are winter crops. Sown Dek, harvested Feb–April. Wheat, barley, gram, potatoes, oilseeds.
Zaid are short summer crops between Rabi and Kharif, April–June. Melons, cucumbers, vegetables.
These seasons underpin agricultural revolutions. Green Revolution first.
Launched 1967–68, aimed to increase yield per hectare. Focused on high-yielding varieties, HYVs of cereals, especially wheat and rice, plus irrigation, fertilizers, pesticides.
Key figures.
Globally, Dr. Norman Borlaug is the father of Green Revolution. In India, Dr. M.S. Swaminathan is credited as the father of Green Revolution in India for adapting and implementing it successfully.
White Revolution, milk production.
Achieved through Operation Flood starting 1970. Aimed to increase milk quality and quantity, make India self-sufficient. Done in 3 phases up to 1996.
Father of the White Revolution.
Dr. Varghese Kurian, the milkman of India, transformed India's dairy industry.
Let's shift to economic geography. Sectors, resources, how we organize things.
Economic activities are just how people earn a living. Shapes, land use, settlements, development.
Primary activities, extracting resources.
Agriculture, fishing, forestry, mining. Pearl culture, too, cultivating pearls. Forms the base, especially in rural areas.
Secondary activities, manufacturing.
Transforming raw materials into finished goods. Textile production, steel making, construction, brick making, industrial processes.
Tertiary activities, services.
Providing services. Includes exchange activities, transportation, communication, banking, education, healthcare, retail, postal services.
And tourism is huge in this sector.
Yes, the world's single largest tertiary activity by jobs, 250 million, and revenue, 40% of global GDP. Drives infrastructure, retail, crafts, souvenirs. Doesn't process raw materials itself.
Quaternary activities, knowledge base.
Highly skilled, information-focused, IT, research and development, even creative fields like professional singing if it involves innovation and composition. Knowledge is an economic driver.
What about settlements? Rural versus urban.
Rural settlement. Most people in primary activities, farming, fishing, etc. Influenced by physical features, terrain, water, cultural factors, social structure, religion, security needs.
Urban settlement. People depend on non-primary activities, manufacturing, services, banking, etc. Census of India has criteria. Municipality status, min population 5,000, 75% male workers in non-agri jobs, density over 4,000 sq kilometers. Okay, minerals in India, natural wealth, iron.
Huge deposits. Bihar, Orissa, MP, Karnataka, Maharashtra. Mines like Singham, Mayurbhanj feed steel plants, Jamshedpur, Bhilai, Bokaro,
Coal, black diamond.
found in Bihar, West Bengal, Damodar Valley, Orissa, AP, MP, Aria, Bihar, and Raniganj, West Bengal are the largest mines. Also used for chemicals, dyes.
Petroleum, black gold.
Found at Digboy, Assam, Ankaleshwar and Kalol, Gujarat, Bombay High, offshore, important note. Jamnagar, Gujarat is the world's largest refining complex, but not an oil field itself.
Manganese for steel.
India is a large producer, found in Orissa, Karnataka, MP, Maharashtra.
Mica, India is the world leader.
Largest producer of mica in the world. Huge deposits in Bihar, Gaya, Hazarba, also AP, Rajasthan. Much is exported.
Aluminium from bauxite.
Light hard metal. Bauxite found in Bihar, Orissa, MP, AP, Karnataka, Tamil Nadu, Maharashtra.
Copper found where?
Good conductor. Used in alloys like brass with zinc, bronze with tin. Found in smaller quantities, mainly Khetri, Rajasthan, some in AP, UP, Tamil Nadu.
Gold, Kolar.
Produced from mines at Kolar and Huti in Karnataka, Anantapuram in Andhra Pradesh. Kolar Goldfield, KGF, is famous.
Diamonds.
Found in mines at Panna in Madhya Pradesh. Buttermine also has large reserves.
Rajasthan seems important for minerals. Gypsum, silver.
Yes, Rajasthan extracts a major share of India's gypsum, 94%, and silver ore, 76%. It's the second largest mineral-producing state, holds about 90% of total mineral reserves, big in non-metallic minerals, and it produces all of India's zinc and much copper.
How do we measure progress beyond just resources? Human Development Index, HDI.
An important measure from the UNDP, created by Mahbub-ul-Haq in 1990, focuses on people, not just economic growth. Key indicators are health, life expectancy, education, schooling years, and standard of living, GNI per capita.
Right.
What's not an indicator?
Birth rate.
Exactly. Birth rate is not an indicator of HDI.
Other measures of economic development.
It's a long-term process. Measures include GDP, poverty incidence, green index, environmental sustainability, life status, literacy rate, average life expectancy. But geographical conditions are not a measure of economic development itself.
Interesting point. Let's touch on urban development during British rule in India. They planned specific types of towns.
Yes, cantonment towns.
Yeah.
For troops under European command, often separate civil lines for Europeans. Meant to be secure, ordered urban models.
Railway colonies.
With railway expansion, first trained in 1853, Bombay Fane, workshops and colonies grew up around them, like Jamalpur, Waltair.
Hill stations. Strategic.
Initially linked to army needs, Simla, Madhabu, Darjeeling, became strategic places for troops, guarding frontiers, launching campaigns, and later resorts. Distinctive colonial feature.
What about model towns? Were they planned by the British?
No, the sources suggest model towns were not specifically planned and developed during the British rule in India, unlike the other types.
Good distinction. Any key economic geography theories we should mention?
So foundational ones, von Thunen's model, 1826, agricultural location theory, explains where different types of farming happen relative to a central market, based on transport costs and land rent. His book was The Isolated State, linked to rent theory, RYPC, FYM formula.
August Lesch, industrial location.
His theory, 1940, focused on finding the optimal location for industries to maximize profit. His big work was The Economics of Location, seminal in regional science.
Doy's method, crop combinations.
Related to mapping crop combination regions, 1959, helps understand agricultural diversity and patterns. It was a modification of J.C. Weaver's earlier method.
And Kristallers' central place theory.
Classic Theory, 1933, explains the spatial arrangements and distribution of human settlements, why towns and cities are located where they are, their size, and the services they offer, based on population thresholds and travel distance. Based on his study of southern Germany, found laws of geography of settlements.
Okay, let's wrap up India with transportation. Indian railways, huge.
Immense. Largest in Asia, fourth largest in the world, the biggest departmental public undertaking in the country.
Key milestones, first train.
Bombay to Thane, 34 kilometers, April 16, 1853. Second train, Howrah to Hooghly, 1854. First electric train. Deccan Queen, Bombay Pune, 1929.
Electrification.
Indian Railways has the second biggest electrified system in the world after Russia.
Headquarters. Fastest train at source time.
HQ in New Delhi. Fastest at the time of the source material was the Shatabadi Express, though faster trains exist now.
Finally, some quick India facts and general knowledge snippets. Area. Bordering states.
The area. 32,087,263 florica kilometers. Uttar Pradesh borders the maximum number of states, 8. Assam borders 7.
Key lines crossing India. Tropic of Cancer.
Passes through 8 states. Gujarat, Rajasthan, MP, Chhattisgarh, Jharkhand, West Bengal, Tripura, Mizoram.
Indian Standard Meridian for
Passed through 5 states: UP, MP, Chhattisgarh, Orissa, Andhra Pradesh.
Coastline. How many states? Longest.
10 states form the coast. Includes Gujarat, state with longest coastline, Maharashtra, Goa, Kerala, Tamil Nadu, Andhra Pradesh, longest coastline of South India, Orissa, West Bengal. Also 2 UTs, Daman and Diu, Pondicherry. Andamans and Lakshadweep are island UTs.
Highest awards, civilian, gallantry.
Highest civilian, Bharat Ratna. Highest gallantry, Paramveer Chakra.
River records. Longest in India. Longest tributary, longest southern river.
Longest river, India. Ganga. Longest tributary, Yamuna. Longest river of the south, Godavari.
Longest estuary former. Deepest river records.
Longest river forming estuary, Narmada. Deepest river valley, Bhagirathi and Alaknanda.
Lake records. Largest freshwater, saline. Highest, man-made.
Largest freshwater, Wooler Lake, Kashmir.
Yeah.
Largest saline water, Choka Lake, Orissa. Highest lake, Devtol Lake, Garhwal. Largest man-made lake, Govind Falab, Pant Sagar, on Rihand Dam.
Mountain landform records. Highest peak. Largest delta. Dams. Waterfall.
Highest mountain peak in India controlled territory disputed. K2 is often cited but complex. Kanchenjunga is highest undisputed in India. K2, Karakoram, is higher but in disputed territory. Largest delta, Sundarbans Delta. Highest dam, Terry Dam. Highest straight gravity dam, Bakra Dam. Longest dam, Hirakud Dam, Orissa. Highest waterfall. Sources vary. Jagarsapa Falls, Karnataka, often cited as one of the highest plunge waterfalls.
City-state records. Largest populated city. State. Pop. Smallest state pop. Densest. Largest state area. Smallest state area.
Largest district?
Largest populated city. Mumbai. Largest state population. Uttar Pradesh. Smallest state population. Sikkim. Densest populated state. Sources vary. Often Bihar or West Bengal depending on your methodology. Largest state area. Rajasthan. Smallest state area. Goa. Largest district. Gujarat.
Infrastructure, longest river bridge, road, canal, highway, platform, electric rail. Longest river bridge, Bhupen Hazarika Setu, Assam. Longest road, Grand Trunk Road, historic. Longest canal, Indira Gandhi Canal, Rajasthan Canal. Longest highway, NH44. Longest railway platform, Hubballi Junction, Karnataka, surpassing Gorakhpur and Kharagpur. Longest electric railway line. Sources mention Delhi to Kolkata via Patna. Longest tunnel, Adel Tunnel, often cited now, surpassing Jawahar Tunnel.
Other largest, highest: museum, cave temple, gateway, hotel, port, church, beach, airport, river island, planetarium, animal fair, battlefield, forest state, corridor. Bridge type.
Largest museum, Indian Museum, Kolkata. Largest cave temple, Kailash Temple, Ellora. Highest gateway, Buland Darwaza, Fatehpur Sikri. Biggest hotel, Oberoi Sheraton, Mumbai, was historically cited. Many large hotels now. Largest port, Mumbai, historically, JNPT or Mundra, often cited now by volume. Largest church, St. Cathedral, Goa. Longest beach, Marina Beach, Chennai. Highest airport, Leh, Ladakh. Largest river island, Majuli, Brahmaputra, Assam. Largest planetarium, Birla Planetarium, Kolkata. Largest animal fair, Sonapur, Bihar. Highest battlefield, Siachen Glacier. Largest forest state, Madhya Pradesh. Largest corridor, Rameshwaram Temple Corridor. Largest cantilever span bridge, Howrah Bridge, Kolkata.
And some place nicknames for fun. Devbhoomi, City of Castles, Dakshin-Ganga, Egg Bowls, Soya Region, Manchester of South, City of Nawabs, Queen of Arabian Sea, Queen of Mountains, Sacred River, Hollywood of India, State of Five Rivers, Boston of India, Garden of Spices, Abode of God, Blue Mountains, Space City, Silicon Valley, Pink City, Gateway of India.
Wow, that's a list. Devbhoomi, Uttarakhand. City of Buildings, Castles, Kolkata. Dakshin Gangold Ganga, Godavari. Egg Bowls of Asia, Andhra Pradesh. Soya Region, Madhya Pradesh. Manchester of the South, Coimbatore. City of Nawabs, Lucknow. Venice of the East, Queen of Arabian Sea. Kochi, Queen of the Mountains, Mussoorie. Sacred River, Ganga. Hollywood of India, City of Seven Islands. Mumbai, State of Five Rivers. Punjab, City of Weavers. Panipat, City of Lakes. Srinagar, also Udaipur. Steel City, Pittsburgh of India. Jamshedpur, City of Temples. Varanasi, Manchester of the North. Kanpur, City of Rallies. New Delhi. Heaven, Switzerland of India. Jammu and Kashmir, Boston of India. Ahmedabad, Garden of Spices, Kerala. Abode of the God, Prayag, Allahabad. Blue Mountains, Nilgiri. Space Garden, Silicon Electronics City. Bengaluru, Pink City. Jaipur, Gateway of India, Mumbai.
Okay, we've done a deep dive into India. Let's pull back again, look at the broader global geography canvas, starting with the continents and their highlights, a quick world tour.
Sounds good. Asia, the largest continent, 30% of Earth's land. Home to huge mountain ranges like the Himalayas, Karakoram, Pemernat.
Highest point, Mount Everest, lowest, the Dead Sea.
Right. Major rivers, Indus, Ganga, Brahmaputra, Yangtze. Huge plateaus like Tibet, big deserts like the Arabian Thar, numerous islands.
Africa, second largest. Equator runs right through it.
Features the Atlas and Drakensberg Mountains.
Yeah.
Highest point Kilimanjaro.
Yeah.
Notably, the whole continent is a plateau, largely.
And deserts, Sahara.
Sahara, Kalahari, Namib. Important straits like Gibraltar and Bab el-Mandeb. Madagascar is a major island off the coast.
North America, third largest. Dominated by the Rockies in the west, Appalachians in the east.
South America, dominated by the Andes Mountains along the west coast. Aconcagua is the highest peak, home to the Amazon rainforest and river. Atacama Desert is famously dry.
Europe ranks sixth in size.
Lots of history. Bordered by Arctic Ocean, Mediterranean Sea, separated from Asia by the Urals, Caucasus, Caspian Sea. Highest point Mount Elbrus, Russia. Largest river Volga.
Rome, city of seven hills. Vatican City, smallest state. Mont Blanc, highest in Alps.
Australia, smallest continent, also the only country that covers an entire continent. The island continent.
Tropic of Capricorn runs through the middle, discovered by Captain James Cook in 1770.
Surrounded by seas like Timor, Arafura, Great Barrier Reef off the northeast, highest point Mount Kosciuszko, lowest point Lake Eyre, major rivers Murray and Darling.
Grasslands, savannas and downs.
Tropical grasslands are savannas, temperate grasslands in the Murray-Darling Basin are downs. Sydney is the largest city. Tasman Sea separates it from New Zealand.
Antarctica, Earth's southernmost continent, under the South Pole. Coldest, driest, windiest.
Almost entirely south of the Antarctic Circle, surrounded by the Southern Ocean. Highest point Vinson Massif. Lowest point the Bentley Subglacial Trench, deep below ice level. Longest river, seasonal meltwater, Onyx River.
Let's hit some global extremes. Hottest place, coldest.
Hottest, Dalal, Ethiopia, average 34 degrees C.
Coldest.
Plateau Station, Antarctica, average make it 56.7 degrees C.
Wettest, driest.
Wettest. Masinram, India, average 11,873 millimeter rain, driest. Atacama Desert, Chile, almost no rain.
Country records. Largest area, longest coastline, most borders. Largest forest.
Largest total land area, Russia. Largest water area, longest coastline, Canada. Most countries bordered, Russia and China, tied. Largest forest area, Russia.
Important deserts globally. Atacama, Sahara.
Kalahari, Namib, Great Sandy, Australia, Great Victoria, Australia, Taklamakan, China, Gobi, Mongolia, China, Thar, India.
Important geographic lines. Latitudes.
Equator, 0 degrees. Tropic of Cancer, 23.5 degrees. Tropic of Capricorn, 23.5 degrees S. Arctic Circle, 66.5 degrees N. Antarctic Circle, 66.5 degrees S.
Longitudes, prime meridian, dateline.
Prime meridian, 0 degrees Greenwich, sets GMT UTC. International dateline, roughly 180 degrees where the calendar day changes. Basis for time zones.
Political borders, 38th parallel, 49th.
30th parallel divides North and South Korea. 49th parallel forms much of the U.S.-Canada border.
And those mnemonics to help remember stuff, highest peaks.
EVA, K2 AMA, Everest, Asia, Vinson Massif, Antarctica, Aconcagua, S. America, K2 Asia Disputed Territory, Mont Blanc, Europe, McKinley Denali, N. America, Kilimanjaro, Africa.
Ararat, also sometimes used for Asia Minor region.
Major rivers. Tamganga could work for some. Tigris, Euphrates, Amazon, Mississippi, Ganges, Amur, Nile, Godavari, Amur again, needs checking for usefulness.
Latitudes.
Simple one. Cancer up, Capricorn down, relative to equator.
Ring of fire countries.
Japan, USA, can helps recall some key ones. Japan, USA, Canada, Indonesia, Philippines, Chile, Peru, Mexico, etc. A useful prompt. Wow, we've really covered some ground today. From the very beginning, the Big Bang, the formation of our solar system.
Yeah, all the way down to the Earth's core, the shifting plates, those volcanoes and mountains.
Then up into the atmosphere, the winds, the pressure belts, cyclones.
And into the vast oceans, the currents, the tides. And then that detailed look at India, its landscapes, rivers, climate, resources.
Really shows how interconnected everything is, doesn't it? Plate tectonics influences volcanoes, which build landforms, which affect climate, which influences vegetation and soils.
And human activities are woven through all of it. Where we live, what resources we use, how we farm.
It's a dynamic living system. Geography isn't just static maps. It's about these ongoing processes and interactions.
And that's the real takeaway, isn't it? The so what. Understanding these things helps make sense of the world. News reports about El Niño, climate change discussions, resource management debates.
Exactly, it gives you context. You can appreciate the forces shaping our planet and the challenges we face. It's not just facts, it's about deeper comprehension.
So, as we wrap up, here's something for you, the listener, to think about. From the Big Bang's ancient echo to the shifting plates right beneath our feet, what new connections or patterns do you now see in the world?
And how might this deeper understanding, this geographical perspective, reshape how you view our shared planetary home?